In this lesson, we will discuss measuring area and volume. Let's start with area. The idea here is it will build off what we did in the previous lesson, that is, how we measure distance. So here's the question. What happens if you square a unit of distance? For example, a centimeter. What's a square centimeter? Or a foot? What is a square foot? First of all, when we say square centimeters, that means the unit centimeters to the power of 2, or multiply a centimeter by a centimeter. And that's the same thing for any unit, but also for feet. Square feet means feet to the power of 2, or feet times feet. More literally, it means create a square with that unit. So let's do that for a foot. To create a square foot, it means you draw 1 foot going in, let's say, this direction. So this is 1 foot. And then at a right angle, you draw another foot going in this direction. So this is also 1 foot. And then I'll use this symbol here to represent that we have a right angle. To draw the entire square, I'll put a side here that's a foot, and a side here that's a foot. And the space that this thing takes up is what we call 1 square foot. If you remember, to find the area of a square, or really any rectangle, it's this side times this adjacent side. So that is, if you want the area, you would take 1 foot and you would multiply that by 1 foot. Well, 1 times 1 is 1 if we're multiplying all this stuff together, and feet times feet is feet squared. And we'll take this as our definition. So when you see square foot, it literally means the space that is taken up by drawing a square using the unit of feet. And this is true for any unit. Inches, centimeters. If you wanted to construct a square centimeter, you would draw a centimeter going in this direction, so that is 1 centimeter. You would draw another centimeter at a right angle like this. You then enclose it into a square, and the space that this thing takes up is what we call 1 square centimeter. The area is computed the same way. You multiply the adjacent sides together. If you do 1 times 1, you get 1. If you do centimeters times centimeters, that's what we call square centimeters. Let's use this idea for area here in example 1. Example 1 says you need to paint a wall that is 12 feet long and 9 feet high, so just this single wall. I'll label that this side is 12 feet and this side is 9 feet. You also bought a can of paint and it claims that it covers 400 square feet. Will this be enough to paint this wall? The way we would figure this out is determine the amount of area that this wall takes up, and hopefully it's a number that's less than 400 square feet. So, how do we find the area that this wall takes up? Well, we can use the formula that says multiply the adjacent sides of the rectangle together. So it's going to be 12 feet times 9 feet. So if I do that, the area of that rectangle is 12 feet times 9 feet. And to multiply this together, 12 times 9 is 108. And feet times feet is what's left over for our unit. But as we've discussed, we can call that square feet or feet squared. This is less than 400 square feet, so we're good. This is enough paint to paint this entire wall. In fact, you could even do a second coat. Usually the second coat makes it look much better. If you double this, it's definitely still less than 400. Now, what if this was just one wall in a room, and you decide, well, let's actually paint the whole room. So paint the whole room. And we'll assume all of the walls in the room are about the same size. Do we have enough paint to paint 4 walls of the same size in this room? I don't think so. If you do 4 times 108, that is 432, and the units are square feet. You basically add this thing to itself 4 times. So now we have a number that's greater than 400 square feet. So here it will work, yes, we can paint the wall, but over here, no, we can't. Now, this assumes that there are no doors or windows. It could be that, if there were a door or a window or two, this might be perfect to put one coat of paint on all four walls of this room. Well, anyway, now that we've thoroughly looked at example 1, why does this work? Why does taking the product give us a number that tells us the area? Like, what are we actually doing here? Let's check that out next. In example 1, we had a wall that was 12 feet by 9 feet. And we figured out that the area, the space that it took up, was 108 square feet. And the way we figured that out was by multiplying 12 by 9 and saying the units must be square feet. But why did this work? What was really going on when we did this? What we were actually doing when we got this number was literally counting the number of square feet. I added a 1 foot by 1 foot grid to the wall. A square foot means you go a foot in opposing directions. So I'll draw in 1 square foot here. This is 1 square foot. How many of these can you place on the wall to cover it perfectly? Well, you can put 12 going this way, and then you can do that again and again and again until you get up to here. You can go through and count them if you want to. It's just that a faster way to go about it is to say, oh, well, you can fit a total of 12 going across this way, and you can do that a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So the multiplication, what it really did for us is it said, oh, I can fit this many squares, 1 foot squares, on this rectangle. And the number you get is, of course, 108. And 108 what? Square feet. And so we attached this unit to it. This is where the formula for the area of a rectangle comes from. So if you want to find the area of a rectangle or a square, same idea, the area is equal to the length times the width. And what you're doing is just counting how many square units you can fit in this region. So for example 1, I chose to do this in feet. But like I said, you can use any unit you'd like. You can use square centimeters, square inches. So here in example 2, I'd like to convert this. Can we convert 108 square feet into square inches? And can we do this by using dimensional analysis? We'll round our answer to the nearest hundredth as necessary. So we're going to start with 108 square feet, and we want to end up with square inches. If you remember the process for dimensional analysis, the idea is you take this number and you multiply it by a fraction. The goal is to cancel the square feet, so square feet has to be in the denominator. The unit that you want left over is square inches, and that is in the numerator. Your goal is to figure out, well, what numbers do I put here and here? So this is a unit fraction, and maybe I'll add a fraction for this first part too. So what's the conversion factor, and how do you find it? Do you remember a conversion factor from distance that connected inches to feet? I believe it was for every 1 foot that is equivalent to 12 inches. So this is equal to this. How could I use this to not have feet, but have square feet? And then how would that equal something over here that wasn't inches, but square inches? This is an equation. I'm going to do the same thing to both sides of my equation. I'm going to square both sides. Here, I'll square 1, and I'll also square feet. 1 squared is 1, because 1 times 1 is 1, and feet squared is simply feet squared. On the other side, if you square 12 inches, you'd first square 12. That's 12 times 12. 12 times 12 is 144. And if you square inches, that's what we call inches squared. So what numbers would go in this fraction to convert this from square feet to square inches? There are 144 square inches for every 1 square foot. So essentially, I'll put 144 here and 1 here. What happens is we cancel the square feet, and what is left over is square inches. Notice the denominator is just 1 times 1 with no units. We don't need to write the denominator anymore. What we will do is multiply 108 by 144. For convenience, I'm going to do that in my calculator here, and I get 15,552. 15,552, and that is square inches. Now, we ended up with a number that makes sense. I was expecting a much bigger number. The reason is a single square inch is smaller than a square foot, so to balance this thing, this number had to get a lot bigger. Essentially, we found the number of square inches here, and then we just multiplied it 108 times to completely cover this object. Let's get a little more practice converting units. So in example 3, let's start by converting 108 square feet, this time into meters, which is metric. This is English system units. These are metric units. I believe we will need to use dimensional analysis to do this. To start the process, I'll put down 108 square feet. And the goal is you want to multiply this by a fraction where square feet is in the denominator. That way it'll cancel. And in the numerator, we want to end up with meters squared, square meters. So I want this. I'm looking for numbers to go here and here. So this fraction is equal to 1. And I'll again call this first thing a fraction 2. You do not need to memorize these conversion factors. You can easily look these up or they'll be given to you. But I'd actually like to try to figure out what the conversion factor is. From the previous lesson, 1 foot was equal to some number of meters. I mean, it was approximate, but I believe it was 0.3 or 3/10 of a meter. Those two things were pretty much the same thing. How would I get square feet and how would I get square meters? You could square both sides of this thing. On this side, if you square 1, you still get 1. And if you square feet, that's feet squared, which is good. And on the other side, you would square the number 0.3 and also meters, which gives us meters squared. What happens if you square 0.3? Well, 3 times 3 is 9, and there's a decimal point for each number, which means there'll be 2 in your answer. 0.3 squared is 0.09. This will allow us to figure out this conversion factor. For every 1 square foot, there are 0.09 square meters. From here, we can cancel the square feet. The denominator is 1 times 1, which we don't need to write anymore. We are left with 108 times 0.09 and the units that we want, which is square meters. So 108 times 0.09 is 9.72, and this is meters squared. And for the last one in this example, let's convert 7 square centimeters to square inches. So that is, we have 7 square centimeters, so centimeters squared. If we want to end up with inches squared, we have to multiply this by something with square centimeters in the denominator and square inches in the numerator. This has to be a fraction that's equal to 1, and I'll make this first thing a fraction. Again, you will be provided with this conversion factor. You do not have to memorize it, but just to see where it comes from the previous lesson, we had that 1 inch was roughly equal to 2.54 centimeters. If you want to get square inches and square centimeters, you can square both sides. The result will still be equal. In fact, 1 inch squared, if you square 1, you get 1. If you square inches, you get inches squared. Okay, on the other side, if you take 2.54 and you square that, that is 6.4516, and the units are centimeters squared. This now tells me what to put into this fraction. In the numerator, I'll put 1. For every 1 square inch, there's 6.4516 square centimeters. The square centimeters cancel. This time when I write the fraction, I have to include the denominator because it's not just 1. It's actually this number here. The numerator is 7 times 1 times inches squared. So that is 7. Our units are inches squared, and we're dividing by 6.4516. I like to think of this as the numbers, so 7 divided by 6.4516, and the units at the end all by itself. I'm going to do this in a calculator too. And if we're rounding to the nearest hundredth as necessary, which it is here, we get 1.09 square inches. So this is the number of square inches that is equivalent to 7 square centimeters. Now let's move on to measuring volume, again building off of measuring distance. So this says here, what happens if you cube a unit of distance, like for example, a cubic centimeter or a cubic mile? So if you say a cubic centimeter, so that is centimeters cubed, that means a centimeter times a centimeter times a centimeter. You multiply it to itself 3 times. More literally, it means construct a cube using centimeters. I'll draw that over here. So let's say 1 centimeter in one direction looks like this. Definitely not drawn to scale, but here's 1 centimeter. Again, the goal is to draw a cube. Well, I can draw 1 centimeter going in this direction. So here's 1 centimeter, and these are at a right angle to each other. Where does the other centimeter go? It'll have to go back into 3 dimensions, which I'll draw going this way here. So I'll use the dashed line going like this, but you'd also have to go 1 centimeter back. This will allow us to actually draw a cube. So I'm going to do my best. Let's see. So the front will be a square, something like this. This side goes back. This side goes back. So does this. We have to enclose the cube so we get this. And then I'll put dashed lines in here. There we go. That's a cube. The idea is that each side has length 1 centimeter. And the space that this takes up is what we call a cubic centimeter. If you want to find the volume of this, you would do length times width times height. So I'll put L times W times H. And here on the cube, that is 1 centimeter times 1 centimeter times 1 centimeter. If we do 1 times 1 times 1, that's 1. And centimeter times centimeter times centimeter is cubic centimeters. So the space that this takes up is this volume here. There was nothing special about using centimeters. This same idea works for any unit of measurement for distance, like inches, feet, or even miles. Like how big would a cubic mile be? It's kind of fun to think about when you're staying outside, how big a cubic mile is. You'd go up a mile, in front a mile, and off to the side a mile. And the amount of space, the volume that that object would take up is 1 cubic mile. It is quite large. Okay, so now that we've actually defined what it means to be a cubic centimeter, for example, how can you use that to determine the volume of other objects? We will explore this in example 4. Here I have a puzzle. It's known as a professor cube. It's essentially a Rubik's Cube. Instead of 3 by 3 by 3, it's 5 by 5 by 5, so a little bit more complicated than a Rubik's Cube. Now for this one here, each one of these individual cubes is actually a cubic centimeter. So this is 1 centimeter by 1 centimeter by 1 centimeter. If you want to find the volume of this thing in cubic centimeters, you could actually just count how many of those things there are in this picture. So that is, how many of these are down here? Well, for just the top, this top layer here, there's 5 going this way, and you can do that 5 times. So just on the top, there's a total of 25 of these things. And then you can do that 1, 2, 3, 4, 5 times. So that would be 25 times 5, which is 125. So just by counting the number of cubic centimeters, we figured out that the volume was equal to 125 cubic centimeters. You can fit 125 of these things into this space. This is equivalent to using this formula here, where the length, which I'll call this side, this is the length, that is 5 centimeters. The width, that is this distance here, this is also 5 centimeters. And then lastly, the height, which is this is also 5 centimeters. So if you go directly to this formula, the volume is 5 centimeters times 5 centimeters times 5 centimeters. 5 times 5 times 5 is 125. Centimeters times centimeters times centimeters, that's 3 of them, that is cubic centimeters. The other part of this question says, convert that volume from cubic centimeters into liters. I added a conversion factor here, which you don't have to memorize, but we say that the second you get to 1,000 of these cubic centimeters, this is what we call 1 liter. I think we can use this conversion factor and dimensional analysis to convert this into liters. So I'm going to write down 125 cubic centimeters, and I'm going to multiply that by a fraction that has cubic centimeters in the denominator and liters in the numerator. I'll put a 1 here and a 1,000 here. And technically, this is a fraction equal to 1. When you cancel the cubic centimeters, we're left over with just liters as the only unit. And we get 125 divided by 1,000. So this is equal to 125 divided by 1,000, and the unit left over is liters. It turns out here that this is a really easy division problem because we're dividing by a power of 10. What that 1,000 is going to do is take the decimal point and move it 1, 2, 3 places this way. Therefore, in liters, this is 0.125 liters. So to say 125 cubic centimeters is the same thing as saying 0.125 liters. All right, trivia time here in example 5. On average, there are about how many liters of blood in the human adult body? If you were to guess, like I can conceptualize 2 liters because I think of a 2-liter bottle of soda. How many of those are there on average in a human adult body? Well, if you made a guess, I actually looked it up. It's approximately 5 liters. So 2 of those 2-liter bottles and then half of another. How much is this in cubic centimeters? So if you have 5 liters, how would you convert that to cubic centimeters? I need a conversion factor. I need liters on the bottom and cubic centimeters on the top. And as we saw in the last example, for every 1 liter, there is 1,000 cubic centimeters. And I'll make this first thing a fraction here. We can cancel liters. This is nice. The denominator in this case is just 1. I'm not going to write it. We have 5 times 1,000 times cubic centimeters. The number is 5,000. And the unit is the one left over, which is cubic centimeters, if you multiply them together. Between this and the previous example, going from cubic centimeters into liters is a simple conversion. We're really just moving the decimal point. If you're going from liters to cubic centimeters, because the unit is smaller, the number gets bigger, and we move the decimal 3 places to the right. In the last example, we started with cubic centimeters and went to liters. That meant the number got smaller, so we moved the decimal point 3 places to the left. Earlier in the lesson, I referenced a cubic mile, which is a large volume. Why would you need a volume that large? Well, you could use it to talk about how large the Earth is. If you were to guess, how many cubic miles of space does planet Earth take up? It turns out we can actually reason out what this value is if we know a couple of things. First, I looked this up. The radius of the Earth, because Earth is spherical, is about 3,958.8 miles. So Earth, here's Earth, it is a sphere. And from the center out to the surface is this many miles. Another piece of information that would be helpful is, well, if this is Earth and Earth is spherical, is there a formula that tells us the volume of a sphere? And there is. It is 4/3 pi times the radius cubed. So Earth is roughly spherical. This is the approximate radius. And if this is the formula for the volume of a cube, you could take this information, put it here into the radius for this formula, compute this, and the number you get out, I believe, is going to be some number of cubic miles. In my computation, I'm going to use that pi is 3.14. That's a very good approximation. So I'll say approximately equal to. If we plug everything in, that is 4/3 times 3.14 times the radius, which is 3958.8. And actually, I think I'm going to include the units here. I'm going to put miles in here, and that's all cubed. So I'm going to type this all directly into a calculator, and this number is being cubed. But so are the units, the miles. Those are being cubed as well. So let's see. Again, this is something that I would use a calculator for. So 4/3 times 3.14 times, now we have 3958.8, and that's cubed. So to the power of 3. All right, here is the number I get. Let's see, that's 259,752,101,300 approximately. And what are the units on this? This is cubic miles. That is a lot of cubic miles. I mean, 1 cubic mile was huge, and it's this many of them. I mean, how many is this? If we count over, that's here, here, and here. Wow. I mean, maybe I'll just round it so it's an easier number to work with. I guess I'll round maybe to this spot. I think that'll be pretty close. That's 260,000,000,000,000. That is 260 billion cubic miles. So there we have it, the approximate volume of planet Earth in cubic miles. In our last example, we are told a 200-hectare farm is selling for $1.5 million. How many acres is this? And what is the price per acre? Note that 1 acre is about 4/10 or is 4/10 of a hectare. So to start with here, we have 200 hectares. If we want to convert this into acres, I want acres in the numerator and hectares in the denominator. The number should be for every 1 acre, there are 4/10 of a hectare. If we multiply these two together, I'll make this a fraction. We will cancel the hectares, and what we have left over is just the unit of acres. That's 200 times 1 divided by 0.4 with no units in the denominator. I'll write that as 200 divided by 0.4, and the units are in acres. All right, to do that division, you could do that in a calculator, but this is 200 divided by 0.4. If we move the decimal over once for both, this actually turns out to be a pretty easy division problem. How many times does 4 go into 2,000? Well, it goes into 25 times, and then everything else is just going to be a 0 thereafter. That's 500. So the answer here is 200 hectares is the same thing as 500 acres. All right. Now, the second part of this question is, what is the price per acre? So here's the number of acres, and this is the amount that it is selling for. So $1.5 million. I'm going to write that as, if we have $1.5 million, I like to see it with the decimals. That's 1,500,000. So here and here. This is dollars. If you're looking for price per acre, we're really saying this fraction. Take the price, put it in the numerator, and then divide by the size, the acres. So if this is the price and this is the acres, I will construct this fraction. So we have 1,500,000, that's dollars, divided by 500 acres. When we simplify this number, these units will still be in a fraction. You would read that as dollars per acre. To get the answer, you could simply take this number, divide by this one, and you have the appropriate units attached to it. But if you don't want to use a calculator, let's see, we can cancel those two zeros with those two. So this is equivalent to, that's 1,500,000. So that's 15,000 divided by 5. And at this point, we can think of the units as their own fraction. That is dollars per acre. How many times does 5 go into 15,000? It goes into 15 3 times, and everything else is going to be 0. So that's 3,000, 3,000. This is equal to, you could write 3,000 over 1 since you divided 5 into it. You have dollars per acre, but you don't need that divided by 1. You can just say 3,000. And that is dollars per acre. You could also write this as 3,000. You could actually spell out the dollars and then put per acre, and we're saying the same thing, but the amount is this, 3,000. That's the price per acre.